Thank you very much, Adrian. I'm very happy that my talk just followed the excellent keynote by George. So that made my job much easier. I don't have to explain what the variational autoencoder-based encoder is. So some of our work is really kind of based on that framework. I will first talk about a scalable extension of that can produce a kind of layered stream, which is very important in network applications. And then I'll describe a relatively new kind of variation, which is mainly done by my collaborator at Nanjing University, which showed a little bit of gains over the most advanced coder that use the autoregressive context model. And then I will also describe the work on learn end-to-end video compression, also done by Zhang's group in Nanjing University, which has shown performance improvement in terms of the SIM over H.265. And then I'll describe some ongoing, very exploratory work in our group on kind of block-based image compression using sort of side information produced from the current block and denoising using adjacent boundary blocks. And also fairly preliminary in terms of prediction of future frames, not explicitly using optical flow estimation, rather using the emerging type of network that's called deformable convolutional network, which directly predict filters with offset. So this is the framework the previous keynote just explained, so I won't talk much about it. So essentially, you have the main encoder, decoder, and the hyperencoder, decoder. And very importantly, you need to have a very good entropy model, as shown here. So so this work, achieved the performance better than the BPG coder. Well, yesterday we learned that AVF is actually a little better than BPG, so I don't know where the AVF would actually fit in there. So one potential problem with the previous framework is that you have to train a different model for each target bitrate by using a property lambda. So you can put lambda either in distortion or in the rate. Here I put it on the rate. Anyway, by using different lambda, then you get a different model that's targeted for different bit rate. And this means in real applications where you have to transmit images in a very dynamic network which has varying bandwidth, you would have to kind of save multiple models and switch between different models depending on the available bandwidth. And this can have delay issues, or like you may have to require extra model storage. So we looked at how do we produce a kind of learned network that also can operate at different bit rate, particularly a kind of scalable stream where you have a base layer bits and enhancement layer bits, and you can keep adding enhancement layer bits to generate better quality. And well, the idea is actually not that elegant. We just stack multiple autoencoders. So for example, you can think of this top one is exactly the previous model, okay? But using a lambda so that it works at a very low bit rate. So we call that a base layer encoder. And then you take the difference between the original image and what's reconstructed from this encoder, and you run through another autoencoder-based network and choose your lambda properly to generate enhancement layer. And the thing is, instead of always using the kind of a same number of feature channels, we use small number of feature channels in the base layer, and so each layer actually use fewer channels. And like overall, if you add them up for a certain bit rate, it may be similar to a single coder that's targeted for a higher bit rate. So this is, so without going into detail, this is a performance comparison. So in terms of PSNR, So actually, our base coder is using the earlier version of the VAE network by Bailey. So it uses hyperprior, but does not use the context model. So it still does not beat BPG. So the top layer is the red is the BPG. And so this cyan is actually the learned compression by Bailey, okay? 2018 paper using the hyperprior. So the black is our scalable version. Interesting, you can see that, in fact, it's produced similar result at a lower rate range. At higher rate, it's kind of as expected, right? When you have a layer stream, you expect loss of coding efficiency, so it does not do as well. But it's encouraging that we can actually achieve similar performance at a lower rate. I think in part because we intentionally choose fewer channels at a lower rates, whereas the Bailey's coder kind of fixed a number of channels in the latent, and then by kind of adjusting lambda to achieve different rates. Okay, and in terms of sim, so this top curve is our scalable coder, the dashed black, which is optimized for sim or MS sim. As you can see that it actually kind of achieves very similar performance as Bailey's coder throughout the entire range. So now let me talk about this new kind of variation of the Bailey's coder. So in this coder, we instead of using GDN, we do not use GDN. In addition, we embedded this module that's highlighted in red circle, which is known as a non-local attention module. I'll talk about that soon. And we also changed the context model slightly. So the previous autoregressive context model is autoregressive in the spatial domain, whereas along the channels, it uses like all the previous channels through a fully connected layer. And here we use a kind of 3D mask convolution. So you only use kind of previous pixel in the same channel and like adjacent channels in the feature map. So that's a small variation, but let me just talk a little bit about this non-local attention module. So the idea is that you're going to produce attention mask that's going to be multiplied with the features you generated, essentially achieving the kind of goal of unequal bit allocation. So you'll be able to allocate more bits to the more important feature maps. In order to produce this attention maps, we leverage this kind of relatively new thing called non-local networks, which was not our invention. But the idea is that instead of convolution, always use your kind of local neighbors, you kind of compare the similarity of this pixel with all the other pixels in the image and kind of use weighted combination based on that similarity. So we have this non-local network block kind of building this branch that generates the attention map. Okay? And we use multiple residue blocks. So the network structure is slightly different. I think it's maybe a little more complex than the original coder. And we do that attention map both on the main encoder and the hyper encoder. So I think I'm going to skip this part. So in terms of performance, so in terms of PSNR, it's a little hard to tell. So the top yellow curve is our coder. As you can see, a kind of slightly better than the coder by Minen, which is the one that uses autoregressive context model. The color is that little brown, okay? And in terms of sim, again, it's better when both are optimized for sim. okay, consistently over the entire read range. I will say, difference may be very small, and if I try to show you the images, you won't tell. Anyway, here we didn't really compare with the other neural coder. It was mainly compared with BPG and JPEG, and you can see that, I don't know what you can see, hopefully you can. Mainly when you kind of optimize for sim, you retain the texture, the rich texture, whereas when you optimize for mean square error, you have the similar effect like BPG, where kind of the fine textures are blurred. So now let me switch gear to end-to-end learned video coding. So this is a paper not by our group, by Lu, and this is the first kind of end-to-end learned video coder which does everything using learned network. So it has the similar block diagram as the traditional video coding, where you do kind of motion compensated prediction, and then you code the motion field as well as the residual. However, instead of using block-based motion estimation, it uses what's called optical flow net to generate the flow map. And then it uses like kind of the previous VAE-based encoder to code the motion flow. And it also code the residual using the VAE type of encoder. Okay. So this approach actually reported better performance than H.264 in both PSNR and MS-SIM, and was on par or better than H.265 in MS-SIM in high rate. But strangely, it doesn't work well at a lower bit rate. Okay? So again, this is a work mainly by my collaborators group in Nanjing. So instead of following this previous approach where they apply a flow net to generate the flow and then code the flow map as images, they realized in any way, it's only like flow net, the optical flow is essentially extracted from some feature. So instead of generating the flow map explicitly, you can just generate the features, multiple feature map, and then you can apply similar idea as in the VAE encoder, where you can generate hyperpriors and entropy models to code those features efficiently. And then the decoder can use those features to generate the flow map, and you can use the flow map to warp your input previous image to generate the predicted flow. So that's the key difference. And they also applied a very kind of a variation of the entropy model, because we're considering a video frames, their temporal correlation. So essentially, this entropy model make use of not only the spatial correlation and hyperpriors, it also incorporate kind of a history of the past frames using a convolutional LSTM. So essentially using the hidden states from that LSTM encoder as part of the features to feed into the entropy model to generate the probability model statistics. So here are some performance comparisons. So the top green curve is this neural-based video encoder. The black curve is the previous also neural-based encoder. So as you can see that the black curve, didn't work well somehow in the low rate region, right? Whereas the new coder achieves gain consistently over the entire range. And so this was tested in the UVG dataset as well as all the classes of HEVC. I only present a few of them. And this is the average over all the dataset. All right, so those are some of the kind of relatively complete work. I like to talk a little bit about the more exploratory work. The first one is about using the dynamic deformable filters for video prediction. So let me first explain. I sent, this might be an earlier version of the, oh my, I'm sorry. I think I sent Adrian an earlier version, which was not complete. Let me see whether I can just,
The new version.
Can I use my laptop?
Sure.
You have a, wait, this is the,
That
I'm
should
so
work.
sorry, I didn't realize. Oh, I thought I sent you the, that's weird.
Could well have done, maybe. And
Oh, great.
Yeah. so you have about five minutes.
Yeah, I think so. This one should be fairly, this is the right one. Yes, all right, so it works. I'm so sorry. All right, so here I'm just showing you what do I mean by deformable network. So as you can see from some features, it's going to generate an offset field, which essentially says every kind of convolution kernel corresponds to a delta x and delta y. And in the original deformable network, it only generates offset. The filter coefficient is fixed, across all the pixels. And then there's another word called dynamic filter, which actually does not generate fixed offsets, but it generates filter coefficient that varies from pixel to pixel. So you can think of some of the pixel could be 0, so therefore the dynamic filters can be maybe a superset of the deformable filter if you use a large filter size. Okay? And we kind of make use of this idea to do video prediction. So the idea is that, okay, given me frame t, I would like to be able to generate offsets as well as filter coefficients that essentially takes kind of weighted combination of a set of neighbors with a proper displacement to create a new pixel for the frame to be predicted. And in order to generate offsets and filters, we use a LSTM network so that this offsets and filter coefficient make use of the past history of the video. Okay? So this is a result on the so-called moving MNIST dataset. So this is the ground truth video. And here we're showing the predicted video generated through the network for different instances of this. So in this example, we use past 10 frames to predict future 10 frames. So the future 10 frame is actually only depend on the previous 10 frames. So we're not predicting every new frame from the past. So if we do that, we expect to get better results. And we try to see what's happening. This is just visualization of the offset. You can see indeed it's pointing to the kind of mostly the corresponding position in the previous frame. And this is a result on the KTH action data set, which kind of more realistic video. And here we get fairly good result as well. But I think this is in part because this kind of action is kind of recurrent, and maybe it's easier to predict than the more natural complex video. And another ongoing work is this kind of fairly recent, we just started, and actually kind of utilizing idea inspired by debugger when we talk about this work. So here we're talking about block-based image compression. So idea is that suppose I want to compress this block, I can kind of generate some side information about this block. And from this side information, in fact, we use the autoencoder to do that. So from the features generated by the encoder, then we can use the decoder to reconstruct a noisy image. Once we have this, we compare it with the border blocks and apply a denoising network to get a better reconstruction of this. So we need to design both the autoencoder decoder and the denoising network jointly to achieve this. We haven't really spent too much time on how do we code the site information efficiently. So it's not really considered in the current design. We just vary the number of latent features that we generate as site information and see what kind of PSNR we can get. So as you can see, if you use more channels, obviously you can get better performance. This rate here is estimated very crudely, just assuming each bit. So in fact, this is obtained by quantizing the latent feature to just -101, and each one takes 1 bit. And that's how we came out with this number. So if we do context-based entropy modeling, it's likely this will be reduced significantly. Just to conclude, I just like to acknowledge my collaborators. First of all, my students at the Video Lab and Jan Ma at Nanjing University. And the Scalable Compression Network was actually done from a visiting student from Beijing University, Chuanmin Jia. And finally, I'd like to thank the support from the Google faculty research work. Thank you.
Any questions?
Hello, hi. So for the video compression part, how complex the model is and what's the performance?
You mean like a model size?
Yeah, what's the model size and when it runs on a reasonably good GPU, how long does it take to encode a frame? Well, what's the encoder performance?
Yeah, actually, I don't have that information. I'm sorry. I think it might be in the draft that I will look that up. If you send me an email, I'll find out.
Thank you.
Yeah.
So regarding the video coding, what is the bitrate savings compared to H.265? You have showed the chart, but what are the numbers? And my second question would be, do you have a rate allocator, and how accurate is your, you can achieve the bitrate target?
Okay. So in terms of bitrate saving, I guess I don't have the PSNR result. I know the reason we didn't present PSNR was because PSNR is still not outperforming. Okay. Yeah, but here, Sam, you can see, right? I mean, I don't have the. I think there's actually table in the book in the paper, but you can see depending on what you're looking at. Yeah, that would be the kind of savings you can look at it. Yeah. And your other question, I'm sorry, was?
So do you have a rate allocator, like you can give a target bitrate and how accurately it achieves that bitrate?
I think we just sum up the rate for the motion and the rate for the residual.
Mm-hmm.
Yeah. And this one also has an intra-coder. So like for intra, we just use this previous approach I talked about. So all of them are coded using.
Okay, thank you.
Which is, kind of slightly better than the previous work. Yeah.
Okay, thank you.
So your results are averages. Do you maybe know the distribution of the results? Do you have maybe very good results and very bad results? Do you know if in some cases you fail, in some cases you're very good? Like averages are, personally, I find them very poor results because, they're missing, like essentially the outliers, and the outliers actually are the ones that matter, especially with machine learning. Are there cases that, the models completely fail, for example, or are you consistently better than let's say your test like HABC or like ABC?
I don't have that information. I could find out, but on average, I know for the video coder, for all the classes, the curve on average is better for each class, but I don't know about the individual video. Yeah. Again, if you want to send me email, I'll find that out. Yeah.
Okay. Thank you very much.
Sorry about it.
Yeah, sorry about the